begin our tour of the chemistry of All Hallows Eve and Bonfire Night by examining how we might recreate fog. Long used in films and at Halloween events to create an eerie atmosphere, here we see it used to great effect in the film The Others.
So of course for your Halloween parties at home, you've probably got a fog machine. Fog machines use glycol, but as chemists we get to play with this lovely stuff. Liquid nitrogen, 220 degrees colder than the water vapour in the air, and of course even colder than the water vapour out of my lungs. As that water vapour meets that liquid nitrogen, so it condenses and forms this wonderful fog. Let's have a look at it.
People have also made fog using solid carbon dioxide. The reason it makes an eerie, creeping fog is down to the density of the carbon dioxide gas produced as the solid carbon dioxide sublimes to gaseous CO2.
The density of carbon dioxide gas is clear in this demonstration. At the bottom of the beaker you see solid carbon dioxide, dry ice. Floating above is a bubble created from exhaled air. So why does it appear as if suspended? That's a result of a cushion of more dense carbon dioxide gas, a product of the sublimation from the solid. Exhaled air is mainly nitrogen, about 16% oxygen, 4% carbon dioxide, the rest noble gases, and is as a result less dense than the carbon dioxide gas underneath, and so it appears that the bubble floats.
So we've already seen that carbon dioxide gas is more dense than air. What I'd like to find out is what happens when you put carbon dioxide into water. I've got some distilled water here, let's pop some in. I've just added a light underneath so that you can see a little bit more about what happens. I'm going to put some pellets in. Now what I'm expecting is that the pellets there'll be greater surface contact between those pellets and the water, and so they'll warm up more quickly. And of course we've got excess water there, and so what we see is as that minus 78.5 carbon dioxide meets that warm water, that 25 degrees-ish water, so we've got the carbon dioxide gas coming up, the water vapour is condensing, we get this wonderful fog. And what you can see is, of course, that fog is coming down, and that's because the carbon dioxide gas is more dense. Remember, it's really important to realise that the white is the water vapour and not the carbon dioxide gas, because otherwise you'd see my breath come out as white.
We can trap our fog and carbon dioxide gas in the bubble mixture from earlier. It's the evolution of that gas that provides the force to inflate our bubble. Eventually, of course, the bubble's surface tension can no longer contain that upward force and the bubble pops. If we apply a lit match, we see how quickly it is extinguished by the mixture of carbon dioxide and fog, that mixture travelling downwards, of course, because of the density of the carbon dioxide gas.
Of course, the use of carbon dioxide to create an atmosphere can have tragic consequences. In early 2020, a Russian internet influencer placed 25 kilos of dry ice into a swimming pool. The result was that 3 people lost their lives as the denser carbon dioxide gas displaced the oxygen.
A well-known aspect of Halloween is the disguise, and in particular the Halloween mask. It's thought that mask wearing dates back to the Celtic festival of Samhain, where a mask was worn to ward off and misdirect spirits. Whatever the origin, a good mask certainly hides the wearer. But what are these masks made of? Well, the cheapest is a simple thermoplastic, a polymer called polystyrene. The most common form is made by a free radical polymerization mechanism, producing this disordered arrangement of the benzene rings along the polymer backbone. Of interest in medical applications, because changing the stereochemistry, or the arrangement, changes the properties, is syndiotactic polystyrene shown here. You can see that there's an order within the chain, and this results in a polymer that is both stronger and more resistant to heat and chemicals. Back to our atactic polystyrene. How do we get a cheap Halloween mask? Well, it's a very simple process called vacuum forming, and you can even set up your own machine if you enjoy making things. You'll need a polystyrene sheet, a mould of your mask, a heater to soften that sheet, and a way of removing air to create the vacuum. So why does it work? Well, Polystyrene is a thermoplastic, and we can alter its shape through heat. The polymer chains are held together by intermolecular forces rather than crosslinks. These are relatively strong. I mean, after all, the sheet is a solid at room temperature. But as you heat that polymer, so you supply enough energy to the chains to overcome some of those intermolecular forces, and this allows them to be more mobile. Using a vacuum or finding a way of removing the air around the mould, you draw the sheet down over that mould, and so you're reshaping the polymer. Of course, you've removed the heat source, and so there's less energy, and the chains become less mobile, and thus they retain their shape once cooled. You might also have come across expanded polystyrene. In this case, the gas pentane is blown through the polystyrene during manufacture, and it ends up, after gas exchange, being about 98% air and 2% polymer. It's a really handy packaging material because of its low density, but it can also be used to decorate your Halloween party. In this case, we're using a solvent, acetone, to partially dissolve the polystyrene chains and release that air. It gives a rather pleasing and gruesome effect. Perhaps it's easier to see what's happening if we take some of those packaging pieces and compare that to our non-expanded polystyrene sheet that we talked about earlier with regard to masks. You can see the rapid dispersal of the air on the left and those bubbles forming. On the right, the sheet softens over time and the dye leaks into the solvent. It's much less dramatic, of course. If we left both for longer, we would end up with a polymer sludge at the bottom of each beaker. Yet perhaps the scariest part of Halloween is the sheer volume of plastic waste that is generated. It's the equivalent of 83 million plastic bottles. Of course, science may come to the rescue. In 2015, it was discovered that mealworms can digest expanded polystyrene. Unfortunately, given their average consumption in a day, it would take nearly 150 million of them a whole year just to chomp through the waste from that one evening. A definite stalwart of Halloween makeup is blood. You can buy fake blood or make your own. In the Harry Potter film, Chamber of Secrets, the production company had to create an entire reproduction of Gloucester Cathedral walls, shown here, so that the fake blood didn't stain the centuries-old stone. For us humans, it's the red colour of blood that gives us the wobbles. Here we've created this blood effect using a simple ligand exchange reaction. Our iron 3 solution turns this blood red colour when we add thiocyanate ions. In the resulting product, we're mimicking the colour seen when the iron-containing haemoglobin, found in our red blood cells, binds with oxygen. Yet other animals have different coloured blood. Squid, for example, have blue oxygenated blood due to the copper-based complex hemocyanin. Peanut worms have purple oxygenated blood due to hemerythrin, whereas the feather duster worm has green blood due to chlorocrurin. Of interest are reptiles living in New Guinea which have green blood. In this case, it's because they have high levels of biliverdin in their blood. This masks the red haemoglobin. Biliverdin is a molecule produced when haemoglobin is broken down. You can see the lack of the metal ion in the centre. We produce it in our bodies too. If you've ever had a bruise, that greenish hue is a result of biliverdin. By the way, the yellow is a product of bilirubin, which is a product of biliverdin being broken down, which is all a part of our red blood cells being broken down, which they are about every 120 days. But even at its highest levels in the human body, when you might be diagnosed with jaundice and the whites of your eyes turn a rather scary yellow colour, you'll still have levels of biliverdin 40 times lower than that of the New Guinea skink. From green blood to green slime. As with blood, we have a natural aversion to slime, and this has been successfully used by filmmakers and authors to fill us with horror. Let's catch up with a recent reimagining of that slime fest, Ghostbusters. In this scene, we join our protagonists in a haunted mansion.
Okay, somebody really doesn't want us getting in that door.
Can you tell us what it's like to walk around in those shoes all day?
It's not fun.
All right.
Oh, Ultra, check this out.
Hold your ponies.
With the slime introduced, let's cut to the ghostly encounter.
It's okay, she seems peaceful. Hello.
I think you're gorgeous.
Hello, hi. My name is Erin Gilbert, Doctor of Particle Physics at Columbia.
The production crew made up a huge vat of slime to film this scene, and this was connected via a hose with a pump to create that jet of slime. The main ingredient in this slime is tapioca. In the chemistry lab, we can make slime by using a soluble polymer, polyvinyl alcohol, or PVA. This consists of long-chain molecules with many alcohol groups along the backbone. It's soluble and it flows well, as you can see as I swirl it with food colouring. If we take another chemical, called borax, then we create these temporary crosslinks across the PVA chains, and this prevents the long chains from flowing as easily, and gives us this wonderful part solid, part liquid slime consistency, that ooze that we really enjoy about slime. In many explanations of the underlying chemistry, we see a depiction of hydrogen bonding as the reason for the crosslinks. But in actual fact, chemists think this isn't quite correct. Boron NMR data suggests it's actually the borate ester linkages that are responsible for these dynamic crosslinks. Borax crosslinking has a serious side too. These borate esters are the crosslinks in hydraulic fracking fluids made from guar gum. But for most of us, slime is simply a Halloween favourite. So whilst we might think of Halloween as a secular festival, its origins are from All Hallows Eve, the beginning of All Hallowtide, and the period when the Catholic Church in particular remembers the dead. You may be familiar from the Disney film Coco or the Bond film Spectre with the celebrations of the Day of the Dead. You might also have carved pumpkins for Halloween, which is great fun. Carving of pumpkins is attributed to Irish folklore and the tale of Stingy Jack, who diddled the devil, yet for his misdemeanours was doomed to roam the earth with only a hollowed out turnip containing a glowing ember to light his way, a jack-o'-lantern.
We're going to use this to showcase our colour chemistry. I've got here a yellow Bunsen flame. That's what you might find if you put a candle into your pumpkin. I've taken the top off so that we can turn up the flame and also turn it to blue.
And you get these fantastic colours. But what's happening? Well, as you pass that salt through a flame, you're providing energy, and that energy will promote an electron from an occupied orbital to an unoccupied orbital. And as that electron falls back to its ground state, so energy is released. And that energy has a particular wavelength which lies within the visible region and corresponds to a particular colour. And it's this aspect of chemistry that is utilised in fireworks. So all these beautiful colours that we see in our firework displays. Of course, whilst the metal salt gives the colour, when we use fireworks, we have to get them into the sky. And for that, we actually use gunpowder or black powder. And records suggest it was Chinese inventors who came up with this mixture of charcoal, sulphur and potassium nitrate. In actual fact, the Chinese were looking for the elixir of life, or the philosopher's stone. Unfortunately, they ended up creating a potent harbinger of death. However, they also realised its benefits in celebrations and fireworks, and records suggest that it was used for this purpose as early as the 1200s. The potassium nitrate, an oxidizer, donates oxygen to the mixture, and this redox reaction is very exothermic, releasing a lot of energy, and so producing gaseous products which build up pressure inside the tube and so fire that firework into the sky.
So the key to a good explosion is to have a rapid production of gas, because that expansion causes a lot of damage. We're going to do that here by putting liquid nitrogen at minus 200 degrees Celsius alongside just freshly boiled water at about plus 100 degrees. So that's a difference of 300. That should cause that liquid nitrogen to turn to gas very, very rapidly. Let's see what happens.
This use was adopted in the West later, as you can see from the panel shown, which is housed in the British Museum. We see a colorised version, with the panels on either side detailing the types of fireworks being used on the Thames back in 1749. It is worth noting that the colorised version has the fireworks as universally gold in colour, and that's a result of gunpowder burning. It took a French chemist, Claude-Louis Berthollet, to give us the colour chemistry we love in modern fireworks, as he discovered potassium chlorate, a more powerful oxidising agent than potassium nitrate, and this allowed the reaction to release even more energy to promote electrons and so produce those beautiful colours.
Now, as our fuel here, I'm going to use a small mass of glucose, the fuel that fuels human beings and other animals and plants, in fact. Glucose, simple sugar, C6H12O6. The oxidizer I'm going to use is also a white powder, and I'm going to use roughly the same mass of that. Now, the problem is, of course, that we've got one white powder on top of another, and if we don't mix them intimately, you may as well have left them in their own containers. So I'm going to use this piece of wooden spill here to mix them up. So I've got an intimate mixture of an oxidizer with a fuel. To get this going, to provide the activation energy, I need to set up a side reaction using concentrated sulfuric acid as our catalyst. So I'm just going to add a few drops of this. In the reaction just seen, we use concentrated sulfuric acid to start the reaction, a redox reaction. Here we're using potassium iodide to speed up the decomposition of hydrogen peroxide to water and oxygen. This redox reaction occurs very slowly at room temperature, but the catalyst, which is actually the iodide ion, speeds up the reaction with a pleasing effect if situated in a pumpkin. The presence of oxygen can be shown with the relighting of a glowing splint.
So, of course, one of the brilliant things about fireworks and gunpowder are the noises that go with it. And if you go to professional firework displays, they will often have a very noisy cannon fire going on in the background, and particularly with those fireworks that are hugely loud. And you'll also find that they play music, often Tchaikovsky's 1812 finale at the end. We're going to do a little bit of cannon fire here. I've got here some hydrogen peroxide, which I'm going to pop into this mortar. And some ethanol. Okay, so hydrogen peroxide and ethanol. Let's light that and see what happens. And if we dim the lights, we see that lovely blue complete combustion flame. That's not very exciting. However, I'm going to add here potassium manganate 7, lovely oxidizer. Let's see what happens. Let's take the flame away. Let's see what happens as we add this. I'm going to add it from above and try and get my hand out of the way. And I think we'll have the lights down as we add this.
We can also create bangs by placing a reaction that produces a large volume of gas into a sealed vessel. The rapid evolution of heat and gas bursts through the weakest part of that vessel, and we see this used to great effect in theatrical devices that uses magnesium powder, an oxidizer and an electrical ignition system, which produces fine magnesium oxide powder or smoke with a bang. Perhaps not truly Halloween or bonfire night chemistry, but rather Christmas panto territory. Let's get back to bonfire night and the ubiquitous sparklers. Using the same oxidizers in fireworks, the reaction is the burning of fine metal powders which react with the oxygen to produce metal oxides. These appear as smoke as they are solids, even at the high temperature of the sparkler burning. The sparkle is a result of the ejection of the burning metal, Again, the rapid evolution of gas forcing the metal powder out of the mixture on the stick. That mixture includes a binder to keep it all together before it's lit.
So in terms of chemistry, a bonfire, of course, is an example of incomplete combustion. But what does that actually mean, Tim?
Well, we have incomplete combustion here in our yellow Bunsen flame. It means that all the fuel is being oxidised straight to carbon dioxide and water. The yellow flame that's there is a result of the formation of carbon rather than carbon dioxide. So we're not getting the heat out of the carbon burning to carbon dioxide, so it's not very efficient. And those carbon atoms, when they're hot, will glow yellow. Let's have a look at some complete combustion. So what I've got here is the fuel for drag racing cars. This is the alcohol methanol CH3OH, and we've got a 20-litre water canister. Let's use the fuel as methanol and the canister as our reaction vessel. I'm just going to shake this up because one thing most people don't realise, it's only vapours or gases that burn, not liquids. So shaking this up will turn some of the liquid into a vapour, and that will fill the canister. I'll just get rid of the surplus fuel. Then we'll just drain out any bits of liquid that haven't vaporised. The vapour is roughly the same density as air, so it's not going to fall out. So in there now we have a fuel-air mixture, and fuel-air mixtures are explosive. We'll add a bit of activation energy to our fuel-air mixture and see what happens. Take note of the colour of the flame. Blue flame, a sign of complete combustion. We're getting all the energy out of the fuel-air mixture that is available to us. And when that finishes, we'll just show you that one of the products of combustion that you don't see in bonfires is the fact that you make water, because of course the bonfire is hot enough to turn that water into vapour that you don't see.
So one of the things for bonfire night is that obviously we do want to have that yellow flame, that incomplete combustion. And the way we can do that is having less oxygen or more fuel. And that's what we've done here. We've captured methane, a fuel, without oxygen, not like methanol that has that extra oxygen. So methane, and we're going to just excess of methane, and we're going to hopefully see that lovely luminous yellow flame as we pass it along.
Ta-da! The bonfire was an outward celebration that King James I survived the plot by Guy Fawkes and his co-conspirators to blow him up along with the Houses of Parliament. That was in 1605. As you huddle around a bonfire on November the 5th, you might encounter people wandering the crowd selling glow sticks.
So of course in your commercial glow sticks you have the chemicals separated. One chemical surrounds a small thin glass vial that contains the other chemical, and the way in which you activate it or mix the chemicals, they have to mix to react, is by snapping it. And as you snap that, so you can see, you can shake it and mix. And so you have that mixture giving you that wonderful colour.
This is another redox reaction involving hydrogen peroxide, but this time it's reacting with diphenyl oxalate to form 1,2-dioxetane which quickly decomposes to carbon dioxide. This releases sufficient energy to excite electrons in the dye molecules. As with our metal salts, when these excited electrons fall back to their ground state, they lose energy in the form of photons of light of a particular wavelength, which corresponds to a perceived colour. In this case, it's a chemical reaction which causes the emission of light, and so it's termed chemiluminescence.
Chemiluminescence is used by chemists when undertaking forensic work at crime scenes. Usually, a mixture of luminol and hydrogen peroxide is used. In the presence of heme, as in the heme in haemoglobin in our blood, a glowing blue colour is seen. Unfortunately, it is sensitive to oxidising contaminants, such as those found in household bleach. In fact, I'm using bleach here to make the luminol glow. In 2017, Chinese chemists substituted an anti-malarial compound called artemisinin for the hydrogen peroxide, and this gives rise to a much more sensitive test for the presence of bloodstains. And that's even if those bloodstains are 100,000 times more dilute than the original deposit, because, say, the perpetrator has attempted to wash away the evidence of their crime. And so we finish with a consideration of the humble match, without which so much of our celebrations of Halloween and Bonfire Night just couldn't happen. The first friction light, a mixture of chemicals which ignited on being struck in some way, was invented by a chemist, John Walker, in 1826. Unfortunately, he decided against patenting the idea, and so in 1829, Samuel Jones launched his own brand of matches called Lucifers, which became the common name for these strike-anywhere matches, despite the differences in composition between manufacturers. And they were aptly named. By 1831, white phosphorus was used in these incendiary devices, and in 1895, worldwide production of phosphorus-based matches had reached 3 trillion. Here we see white phosphorus burning in oxygen, an absolutely stunning reaction, giving off an extraordinarily bright light. The inclusion of white phosphorus in matches gave people a portable and extremely easy way of producing fire. However, these light bringers were also hellish. Women and girls working in the factories producing these matches suffered from phosphorus poisoning. This resulted in necrosis of the jaw. Literally, the jawbone was eaten away. Symptoms would start off with toothache, then the teeth would fall out, the face would swell up, and abscesses along the jaw would ooze the most foul-smelling pus. Holes would open up in the face along the jawline, through which you could see the dead bone underneath. Sometimes the bone even glowed in the dark from the accumulated phosphorus. And the only option was to remove the entire jawbone. It took until 1906 for the use of white phosphorus in matches to be banned at the International Convention in Bern. Red phosphorus is now used in safety matches, which have the reactants separated between the match head and the striking surface.
We hope you've enjoyed our chemical tour of All Hallows Eve and Bonfire Night. If so, get in touch and let us know your thoughts on the exciting reactions that underpin our celebrations.